Okay, so now I want to just do a worked example which is very similar to an A-level question. Afterwards I'm going to explain why I'm doing the things I'm doing, but to start with I'm just going to do them. So now let's consider a matrix 2, 3, minus 1/2, minus 1/2. I want to calculate the eigenvalues and eigenvectors of this matrix. Our first task is to calculate the characteristic equation. So the characteristic equation, if I call this matrix M, is the determinant of M minus lambda lots of the identity. Let's substitute in what M is. So this will be the determinant of 2 minus lambda, 3, minus 1/2, minus 1/2 minus lambda. It's a 2 by 2 matrix, so we know the determinant immediately. 2 minus lambda, minus 1/2 take lambda, plus 3 upon 2. If I expand that out and simplify, I have lambda squared. I have minus 2 lambda plus 1/2, so that's going to be minus 3 upon 2 lambda. I'll then have minus 1 plus 3 upon 2. That cancels it to give me plus 1/2. Now this quadratic equation factorizes as lambda minus 1, lambda minus 1/2. So the roots of the characteristic equation, the values of lambda where this is 0, is lambda equals 1 or lambda equals 1/2. These are exactly the eigenvalues of our matrix. Once we know the eigenvalues, we can calculate the eigenvectors by computation. So my first eigenvalue was lambda equals 1, so I wish to solve the vector equation mx equals 1 times x. To substitute this in, that's 2, 3, minus 1/2, minus 1/2 times xy is equal to xy. Again, this is going to give me two simultaneous equations, 2x plus 3y equals x, and minus 1/2 x minus 1/2 y equals y. Again, these actually reduce to exactly the same equation, which is simply x plus 3y equals 0. Why don't I rearrange this to tell me what y is? So y is equal to minus x divided by 3. My other eigenvalue was 1/2, so to find its eigenvectors, we need to solve the matrix equation mx equals 1/2 times x. So let's write this out. 2, 3, minus 1/2, minus 1/2 times xy is equal to 1/2 xy. Again, this gives me two simultaneous equations. 2x plus 3y equals 1/2 x, minus 1/2 x minus 1/2 y equals 1/2 y. Again, these two equations collapse to give one equation. Let's use the bottom one for variety. I'll move the half y over to the other side, which conveniently tells me that y is equal to 1/2 minus 1/2 x. So in summary, we found that the eigenvalues were 1.5. For lambda equals 1, we found that the eigenvectors were all of the form x, lots of 1 or minus 1/3. I'm allowed to choose x to be whatever I like, but I'm not allowed to choose it to be 0. Similarly, for lambda equals 1/2, we found that the eigenvectors were all of the form x, 1 minus 1/2. Again, x is allowed to be anything as long as it's not 0. Now let's think about an explanation. Why did I have to calculate the determinant? Why was the characteristic equation useful? We're interested in solving the vector equation mx equals lambda x. And I'm interested in doing this for non-zero vectors x. It's important that x isn't 0. If x is 0, this equation is always true, regardless of what lambda is. And that's, in some sense, too easy a solution to be helpful to us. Well, I can rearrange this as m minus lambda lots of the identity times x is equal to 0. So let's think. If the determinant of m minus lambda lots of the identity is not 0, then we know that the matrix m minus lambda I is invertible. So, if we have such a solution, m minus lambda I times the vector x is 0, then x is equal to m minus lambda I inverse, which we've decided exists, multiplied by m minus lambda I lots of x, because these two matrices cancel out to give me the identity. However, I know that this part here is equal to 0. So this is m minus lambda I inverse times 0, and that is equal to 0. So the only choice is that x is 0, and we decided that that wasn't interesting. So if we wish to solve this equation and find an interesting solution x, the determinant of m minus lambda I has to be 0. That turns out to be enough. If determinant m minus lambda I is equal to 0, then the matrix m minus lambda I is singular. And we know that that means that there is some non-zero vector x with m minus lambda I x is 0. And that's exactly the equation we wanted to solve. So we see that we can solve our original problem, mx equals lambda x, if and only if the determinant of m minus lambda I is 0. And that's why we need to solve this first in order to determine the values of lambda. Let's think about an application of what we just did. Suppose I'm interested in applying the matrix repeatedly to some vector. Well, I can write any vector as a combination of my two eigenvectors, and that will turn out to be very useful. So I start with a vector v. I can always write this as some scalar multiple of my first eigenvector, which was 1 minus 1/3, plus some scalar multiple of my second eigenvector, 1 minus 1/2. Well, if I then apply my matrix M to V, now M commutes with scalar multiples and additions. So this is going to be A lots of M applied to my vector 1 minus 1/3 plus B lots of M applied to the vector 1 minus 1/2. But I can now use that these are eigenvectors, so I know exactly what happens. This is an eigenvector for the eigenvalue 1, so the matrix actually does nothing to it. This second vector is an eigenvector for the eigenvalue 1/2, so B gets divided by 2. So again, with respect to these two vectors, this one stays the same, this one gets shrunk by 1/2. If I do this repeatedly, this one is going to carry on getting shrunk. So, skipping details, suppose I apply m to the power k to v. That's the same as applying m k times. Nothing is going to change in the first. But the second part, I'm going to keep dividing by 2. So I'll end up with b divided by 2 to the power k. If k is large, 2 to the power k is very large, and so b divided by 2 to the power k is about 0. So this is approximately just the first part. So if k is large, I can get a very good estimate of what n to the k times v is equal to, without having to do very much calculation at all. So I now want to go through an actual past paper question applying some of these ideas. So we're going to start with a matrix M which is minus 1, 2, minus 2, 3. And the question tells us that this represents a shear. So with respect to some coordinate system, what this matrix does is pushes everything along in that direction, shearing it. The first part of the question asks, find the determinant of m and give a geometrical interpretation of this result. Well, that's just a calculation. Det m is minus 1 times 3 minus 2 times minus 2. Well, that's minus 3 plus 4, so that's equal to 1. Now, if we remember, the determinants tell us how area changes. So if the determinant of m is 1, geometrically that's telling me that m doesn't change area. Geometrically, m preserves area. We expect that because we're told it's a shear, and shears always preserve area. The question then goes on and asks us to find the characteristic equation, and actually tells us what we're aiming for. So, well, let's find the characteristic equation and then check that we get the expected answer. Characteristic equation is determinant of m minus lambda I. In that case, that's going to be the determinant of minus 1 minus lambda, 2 minus 2, 3 minus lambda. Again, it's 2 by 2, so we can just multiply out. Let's expand that. Lambda squared. I have a plus lambda minus 3 lambda. So that's minus 2 lambda. I have minus 3 plus 4. So that becomes plus 1. And indeed, that is the expected result. We're next asked to find an eigenvector for m. But of course, before we do that, we need to find what the eigenvalues are. That is, I need to find the roots of this equation, the values of lambda where it's equal to 0. Well, this factorizes as lambda minus 1 squared. So the only eigenvalue is 1. So sometimes we don't get two different eigenvalues. We can now find the eigenvector. Again, we need to solve mx equals x. Let's substitute that in. This, yet again, yields two simultaneous equations. Minus x plus 2y is equal to x, and minus 2x plus 3y is equal to y. These collapse down to give me the same equation. Let's move x over here. So I get 2y is equal to 2x. Of course, that simplifies to be x equals y. The question actually just asks us for one eigenvector, so an eigenvector is 1, 1. Or I could choose any non-zero scalar multiple of that. The final part of the question asks us to write down the invariant line for this transformation. Well, we've found that the eigenvector for the eigenvalue 1 is equal to 1, 1, so anything that's proportional to this vector will be left invariant by the matrix. So the invariant line is simply x equals y. Let's think a little bit more about this question. We were told this is a shear, but that's not particularly obvious from the matrix. We've chosen our new x-axis, but there's no obvious choice for what the new y-axis should be, because we only have one eigenvector. So let's choose a vector almost at random. Let's y new be equal to minus 1, 1. I really could have chosen anything as long as it wasn't proportional to my new x direction. So let's think about what the matrix does to these two new coordinate directions. It will leave this one invariant because this is an eigenvector for the eigenvalue 1. So we need to think about what it's going to do to y new. Let's multiply this out. So we have minus 1 times minus 1, which is 1, plus 2, which gives me 3. Then minus 2 times minus 1, which is 2, plus 3, which gives me 5. Well, a little bit of computation will show that that's equal to 4 lots of 1, 1, plus 1 lot of minus 1, 1. Let's just check that. 4 plus minus 1 is 3, 4 plus 1 is 5. So let's think about what's going on in the diagram. On the left-hand side, I'm using the old coordinate system. So I'm starting with this grey rectangle, and that's getting moved to this grey parallelogram. It's not at all obvious what's going on. The red arrow is what my unit x direction gets mapped to, and my green arrow is what my unit y direction gets mapped to. Now let's move to the new coordinate system. Here it's much more obvious what's going on. The red arrow represents my eigenvector, which is fixed. My green arrow represents my new choice for the y-axis, which we decided ended up being shifted 4 units in the x direction. So this is obviously a shear. If I'd chosen a different choice for my y direction, I would have gotten a different shear, but it would still be a shear.